So we're going to talk about power measurement. In a three-phase system. So I'm about to draw a portion of a circuit, and we're going to start by looking at a single-phase circuit because the exact same instrument is used for both single-phase circuits and three-phase circuits, okay? So on the left-hand side here, I'm just putting some ellipses, and all I mean by this is just there's stuff on the left-hand side representing the source, maybe some transmission line impedances, all that kind of stuff. Nothing that we're particularly worried about here, okay? So this is, we're just looking at a portion of a whole network. So I've got some terminal A and some terminal N, and these are the only terminals that I'm going to have because, like I said, we're going to be looking at a single phase network first. Over here on the right-hand side, I'm going to have an uppercase A and an uppercase N representing the terminals of my load. And then here, I simply have my load impedance represented by ZL, okay? So between those transmission line terminals on the left and our load on the right, we are going to put in a network, and that network is what's known as a watt meter, okay? So a watt meter is a piece of equipment that is used to measure the average power consumed by a load. So let's talk about briefly why that's important, okay? So if we were to use a multimeter to measure the voltage drop across the terminals of our load when it's a part of a live network, what would we see? This is not a trick question. So, but it will be expressed in what way? So we have a multimeter. What is it capable of measuring? So it can measure DC voltages for sure. I believe, I'm not 100% sure, that's why I'm looking at Ron, that you guys probably used it to measure AC voltages as an RMS voltage in your previous class, right? So we would be able to use a multimeter to get the RMS voltage across this load if it was part of a live network. If we change the setting on our multimeter and put it effectively in series with the load, I would argue that we would also be able to measure the RMS current flowing through the load, right? So using a multimeter, we have access to the RMS voltage and the RMS current. Well, what's the product of the magnitude of the RMS voltage and the magnitude of the RMS current? Because that's the only thing that we have access to. It's not average power, it's apparent power, right? Apparent power is simply the magnitude of the voltage times the magnitude of the current, okay? A watt meter allows us to get average power, okay? Which is actually a significantly harder thing to measure because it requires us to know what the phase of our voltage and current are, okay? So our watt meter is just a device that contains two coils, okay? So I'm going to put one coil right here, and this plus or minus sign effectively is just telling us what polarity to connect to the source side of things. And I'm going to label this coil as CC. This stands for current coil, okay? So it's the coil that is sensing the current that's flowing into the load. And then we also have a second coil, which I'm going to label as VC. This coil also measures a current, but the current that it measures is proportional to the voltage drop across the load, so we call it the voltage coil. And when we put these two coils together, we have a device that is called a watt meter, which I am effectively outlining in this circuit, in this green box. So the output of a watt meter is simply a readout. It might be a dial gauge or it might be a digital watt meter, but literally the only thing that it's going to tell us is the average power, P, absorbed by our load. So this is what the implementation of a watt meter would look like in a single phase circuit. Now we can expand this to a three-phase circuit pretty simply, right? So let me put a notation here. So this is a single phase watt meter connection. If we had, let's say, for example, a three-phase Y connected load where we have access to a neutral, our total average power could be determined by using as many as 3 watt meters, right? So think about something like this. So here's our A phase. I'm going to give myself plenty of room. So over here on the right-hand side, I'm going to connect my impedance. I'm expressing this as ZYA, ZYB, and ZYC because we can use watt meters to determine the average power in an unbalanced system. So there's nothing specifically requiring us to have a balanced load. Yes. Mhm. That's why, and because I'm going to do 3 of them and I have to make the connection look pretty, that's why I gave myself so much space. So here's ZYB. ZYC. And down here would be our neutral terminal. So B, B, oh, make that look smaller. So our A phase watt meter might look something like this. So here's my current coil. Here's my voltage coil. And it would be placed between the A terminal and the neutral terminal. My B phase watt meter might be over here. Where I have my current coil and my voltage coil. And then my C phase watt meter might be right here with my current coil and voltage coil like so. And just going to outline them in green. So here's watt meter number 1 that tells us the power absorbed by the A phase. Here's watt meter number 2 that's telling us the average power absorbed by the B phase. And here's watt meter number 3 that's telling us the average power absorbed by the C phase. So the three-phase average power would simply be the reading of wattmeter A plus the reading of wattmeter B plus the reading of wattmeter C. And what the wattmeter is really reading is the phase voltage magnitude of phase A. Let me do this as a capital letter since it's across the load, times the phase current of the A phase times the cosine of theta ZYA plus the phase voltage for the B phase, the phase current of the B phase, cosine theta ZYB plus BPC IPC cosine theta ZYC, right? So just phase voltage times phase current times the magnitude or the angle of the impedance, right, is giving us our average power on all three of those phases. We add them together. For a balanced system, our three-phase power then looks like, oh, and actually, let me just put it this way, sorry. This is just going to look like 3 VP IP cosine theta y, which is literally exactly an expression that we derived when we were looking at our power relationships. So let's look at what exactly is going on here, right? So our current coil is effectively sensing this line current, IAA, which is literally the exact same thing as this phase current, IAN, which is why I said it's looking at phase currents and phase voltages. Our voltage coil is connected between the capital A transmission line terminal and the capital N transmission line terminal. So it is effectively measuring this voltage VAN. So in this particular configuration, I'm just trying to be clear about this, all of what the wattmeter is giving us is based on phase voltages and phase currents. Now, why I'm bringing that up is because we won't always have access to those quantities depending on what type of load we have. For example, in a three-phase electrical motor, we will only have access to transmission line terminals, right? We won't have access to the neutral usually. We don't need it by any stretch of the imagination. And also, there's no guarantee that the motor that we're dealing with isn't just wired in delta anyway, where it literally wouldn't have a neutral for us to connect to, right? So there's got to be a different way of measuring things whenever we only have access to our transmission line terminals. And that's what's commonly called the 2-wattmeter method, okay? So, and we can use a 2-wattmeter approach on literally any three-phase network because it only requires us to have access to those transmission line terminals. So while this is fine and dandy, it's limited in its application, and it's also significantly more expensive because it's using 3 wattmeters instead of 2. So realistically, this is never actually done It's simply a representation of how you could go from a single phase watt meter application to doing it with 3 phases. The 2 watt meter method is the one that's used in industry. The unbalanced equation? Oh, balance. 3 BP IP cosine theta y, which is literally just 3 times the thing measured by the watt meters. So in a balanced system, all 3 of those watt meters would give you literally the exact same reading. Correct. For what it's worth, I'm not expecting you to use literally either of those 2 equations. Okay. So because the 2 watt meter method is what's actually used in practice, that's where I want you guys to actually pay attention to the equations and all that kind of stuff. So I'll put boxes around them to note, hey, this is what I'm expecting you to know from this. All right, so the 2 watt meter method. So on the right-hand side of my page here, in just a moment, I am going to draw a generic 3-phase load. So just a big black box, right? We have no idea whatsoever if this load is delta connected or Y connected, because it literally doesn't matter. We also don't know whether it is balanced or unbalanced. So I'm going to put Y or delta, and also balanced or unbalanced. Literally doesn't matter. And I'm going to put my first watt meter here between the A and B transmission line terminals. So here is my current coil. Here is my voltage coil. Like so. So this is watt meter number 1. And it's going to give us some average power reading, which I'm going to call P1. I'm not going to call it PA, B, or C because it's not really for the A, B, or C phase. It's just some average power in the system, and we're going to mathematically define it here in a moment. And then I'm going to have a second watt meter that I'm going to place between the C and the B terminals. So here's my current coil, just in line with my line current ICC that I'll label in a moment. And then here's my voltage coil. And I want you to note that the voltage coil is connected upside down from how we've been doing it. And this guy is going to give us a reading of P2. So just to be explicitly clear about what our watt meters are measuring, the voltage coil is measuring the magnitude of this voltage VAB, and the voltage coil of watt meter 2 is measuring the magnitude of this voltage VBC. Current coil is measuring the line current IAA and ICC. So these 2 watt meters are set up to be measuring line voltages and line currents, right? So we don't need anything for phase voltages and phase currents. Doesn't matter at all. Okay. So we are going to derive how this works for a balanced three-phase load. However, I want you to understand that the method works even if it is unbalanced. Using a balanced three-phase load is going to make the math just way easier to deal with so that we don't have to stumble through 30 minutes of trig identities that neither you or I care about, okay? So the average power that watt meter 1 is showing is nothing more than the magnitude of the voltage VAB times the magnitude of the current IAA times cosine of theta z plus 30 degrees, okay? Where theta z is the angle of the per phase impedance of our load, right? And we are making an assumption here is balanced, okay? The reason why I'm explicitly saying that we're making that assumption here is because that 30 degrees there is only true when it's a balanced system. So let's just talk very briefly about where that 30 degrees effectively comes from, right? So we know that if we have a Y connected load, the line voltage V capital A capital B, and the phase voltage V capital A capital N are related to each other by a factor of √3 angle 30 degrees. If we have a Y connected load, then we know the line current IAA and the phase current IAN are related to each other by a factor of √3 angle 30 degrees. So regardless of whether our load is connected in delta or connected in Y, there's going to be a 30-degree phase shift relationship between the line quantities and the phase quantities. And so that's why I'm adding that 30 degrees to the angle of the impedance, which, to be clear here, we probably don't actually know. Doing something similar, the average power that watt meter 2 is giving us is just the magnitude of this voltage VBC times the magnitude of that current ICC times cosine of theta z minus 30 degrees. And the reason why watt meter 2 is having the minus 30 degrees is because we connected it upside down. Okay? Same relationships, but we connected it, quote unquote, the wrong way. And so it's giving us the wrong phase angle relationship. And we're going to use that to our advantage. Because if I add these two together, P1 plus P2, what I wind up getting is the magnitude of VAB times the magnitude of IAA times cosine theta z plus 30 degrees plus the magnitude of VBC times the magnitude of ICC cosine, theta z minus 30 degrees. Well, for a balanced system, what do we know about the magnitude of VAB and the magnitude of VBC? They are exactly the same quantity. Absolutely correct. So we're going to call that just VL, which is what we've been using to call a magnitude of a line voltage. So we've got a VL. that's common to both things. What do we know about the magnitude of our line current IAA and the magnitude of our line current ICC in a balanced system? Hit me with it again. They're the same damn thing. So we're going to call that just our line current, IL. Okay. So now I'm adding cosine theta z plus 30 and cosine theta z minus 30. Not going to make you guys suffer through the trig identity, but what that's going to look like is twice cosine theta z times the cosine of 30 degrees. So I would like for one of you guys to put in your calculator 2 cosine 30 degrees and tell me what comes out of that. What? I do not agree that it is 1. Square root of 3. Absolutely right. So 2 cosine 30 looks like square root of 3. Then I have VL, IL, cosine theta z. Does this look familiar? If it doesn't, go back to your notes for where we were deriving the power relationships for three-phase systems, because this is literally nothing more than the total average power absorbed by a balanced three-phase network where we have the line voltage and the line currents as a known quantity. This is something that we derived last week. So we get literally the exact same result simply by just adding the two powers that the wattmeter gives us. Okay? So P three-phase is nothing more than P1 plus P2. And I'm going to put a note here. This is true for balanced and unbalanced systems. So our average power is just adding the results of the outputs of those two wattmeters together, regardless of whether we have a Y-connected system, a delta-connected system, whether it's balanced, whether it's unbalanced. That gives us our average power 100% of the time. So a wattmeter is a pretty damn powerful instrument, particularly in a three-phase system. We only need 2 of them to figure out what's going on. Now, let's say that we're working strictly with a balanced system, okay? So oh goodness, that looks like garbage. We know that P1 plus P2 comes out to be twice VL IL cosine theta z cosine 30 degrees. That's literally from right up here. P1 minus P2 is going to come out as -2 VL IL sine theta z sine 30. I'm going to show you in a second why we're expressing it in this way. And I'm about to take the ratio of these two quantities and show you effectively that if we have a balanced system, the 2 wattmeter method, while it's meant to just give us the average power, can actually be used to find power factor. And then if we know the average power and the power factor, we have all of the information that we need to calculate any part of the complex power. So, all right, so if I take the ratio of P1 plus P2 divided by P1 minus P2, I'm going to have twice VL IL cosine theta z cosine 30 degrees divided by -2 VL IL sine theta z sine 30 degrees. So we can see very easily that the VL IL cancels out in both the numerator and the denominator. We know that twice cosine 30 degrees is the square root of 3. So I'm going to put a square root of 3 up here in the numerator. What's -2 sine 30 degrees? -1. So I'm just going to put a negative sign out front. And so just to be clear here, I have lumped this guy and this guy together to get that square root of 3. We lumped this guy and this guy together to get that -1. What's cosine divided by sine? Or what's sine divided by cosine? Tangent. So P1 plus P2 divided by P1 minus P2 is √3 divided by the tangent of the angle of the impedance, which is our power factor angle. So from this, we can simply rearrange and say that theta z, I'm just going to make a note here, our power factor angle is the inverse tangent of the square root of 3 times P2 minus P1. So I changed the order there. So in the line above, I have P1 minus P2, which is the exact same thing as a negative P2 minus P1. That's just me getting rid of the negative signs. Okay. Divided by P2 plus P1. So now, only taking the two readings from our watt meters, we can figure out what our power factor is. So let's work an example here really quickly. And this will be the last thing that I want to cover for today. Sure. So let's say that I have a balanced three-phase load. And watt meter number 1 reads 60 kilowatts. And watt meter number 2 reads 180 kilowatts. I want us to find the total three-phase power as well as the power factor at which the load operates. Okay. So what's our total average power for our three-phase system going to be? 60 plus 180. Yep, just literally add them together. 240 kilowatts. Easiest equation I'm going to give you guys the entire quarter. Okay. Now let's figure out what our power factor angle is. So that's just the inverse tangent of root 3 times P2 minus P1. So what's P2 minus P1? Okay, so 120. And what's P1 plus P2 again? So what is the inverse tangent of root 3 times 1/2? I'm not expecting you to know that off the top of your head, by the way. Calculators are for a reason. 40.893 degrees. Okay. All right, so 40.893 degrees. Now, I just want to remind you guys of something here really quickly. The arctangent operation is capable of giving us a negative angle, which is a good thing because we got 40.893 degrees as a positive number, which means when we calculate our power factor here, we know that it's lagging. There's no ambiguity with this at all, right? So if the arctangent operation gives us a positive angle, we have a lagging power factor. If the arctangent operation gives us a negative angle, we have a leading power factor. There's nothing requiring us to force a negative sign on there because of the way the arctangent operation works, as opposed to the arc cosine operation. So from here, our power factor is nothing more than the cosine of 40.893 degrees, which is 0.756 lagging. And so now that we know average power and power factor, this is enough information to give us the complex power and therefore any power related quantity that we want, right? So from numerous examples that we've worked before, our complex power S would just be, so let's put this as S3 phase, would just be P3 phase divided by power factor with an angle of the inverse cosine of the power factor, which for this particular example comes out to be 317.490 with an angle of 40.893 degrees kilovolt amperes. And that is the 2 watt meter method. All right, so let's talk a little bit about your test on Tuesday. I have already written it. It is 2 problems and a bonus. The first problem is 3-phase circuit analysis. So the kind of stuff that I asked you to do on homework, I guess it would be 6 and 7. Yeah. Okay. So I'm just going to give you a circuit, including the circuit diagram, and ask you to find various quantities. So I could ask you to find line voltages, line currents, phase voltages, phase currents. That's the only thing that I can ask you. So it's going to be some combination of those things. I'm not going to bother with making you find the quantity for all 3 phases because you all know by this point that if you find the A phase, you just subtract 120 degrees to get the B phase, subtract 240 to get the C phase. So as far as the test is concerned, that is a waste of your time. Okay. The second problem will be a power problem, like the ones that we've been working for the last couple of days. So it'll be some large circuit thing with some number of loads. You're going to be given either average power, apparent power, power factors, and all of that kind of stuff. You're going to have to tell me, you know, what complex power is, maybe calculate a power factor, and then there's also going to be some power factor correction related problems associated with that as well, meaning that you're going to have to tell me what, you know, how to find C delta and or CY. The bonus question is what we covered today. Yeah. So there will be 10 total parts, just like your first exam had. There was 10 total questions because there was the 10-point questions each had, 1 part apiece, and then the 20-point questions each had 2 parts apiece, so it was 10 for the exact same thing here. I'm telling you that because you guys took way too damn long taking exam 1, in my opinion. You should have been able to finish that whole thing in my jackass with a PhD opinion in less than an hour. Okay. So I'm not saying if you're not finished with this test in under an hour, you're doing it wrong. I'm telling you, you need to be quick and efficient at working this style of problems because there's going to be 10 things for you to answer. Okay. The best way to review is making sure that you understand the homeworks and the ICAs. Okay. So that's what you should expect to see on your test. All right. So we've got 45 minutes before I need to leave. What do you guys want to talk about?
That's pretty easy. Like, I've seen the big word, like, but I mean, at least I feel like I was better off on the complex tower than I was the other stuff. So like,
Well, I mean, this stuff particular with the 2-watt meter method is pretty incredibly simple.
yeah. So, I mean, I just really need to review the homework too, the homework 7, review the, all the equations and everything.
Yes, so you will be allowed to use a 1-page, standard 8.5 by 11-inch sheet of paper, front and back handwritten, just like exam 1. And I will be collecting it with your test, just like exam 1. Next. There's another homework coming on the power relationships. I have the first 3 problems written. So in my EE classes, usually I just write the problems and then give them to the students and then wind up posting the answers a day or so before they're due. But with you guys, it seems like you won't even start working on them until I give you the answers, so I'm not wasting either of our times. So I expect them to be up by close of business today. Like I said, I only have 2 problems left to write for it. So, yep, and it'll be due on Tuesday. Okay. It'll be due on Tuesday at midnight, which is technically after your test,